So the next part is data pre-processing. So in data pre-processing, we will see the overview. Why pre-process data? Why is it important to pre-process the data? Measures for data quality, a multi-dimensional view, accuracy, correct or wrong, accurate or not. So to check whether the data is accurate or not. Completeness, not recorded, unavailable. Consistency, some modified but some not, dangling. Timeliness, timely update. Believability, how trustable the data are correct. Interpretability, how easily the data can be understood. Major task in data pre-processing. Data cleaning, fill in the missing values. Smooth noisy data, identify or remove outliers and resolve inconsistency. So fill in the missing values, smooth noisy data, identify or remove the outliers and resolve inconsistencies. Data integration, integration of multiple databases, data cubes or files. Data reduction, dimensionality reduction, numerosity reduction, data compression, data transformation and data discretization, normalization and concept hierarchy generation. So we'll learn about data cleaning up. Data in real world is dirty. So in the real world, the data is dirty. Lots of potentially incorrect data, example instrument faulty, human or computer error, transmission error. So there are a lot of potentially incorrect data is present. Incomplete, lacking attribute values, lacking certain attributes of interest or containing only aggregate data. So occupation equal to nothing that is the missing data. So incomplete data can be a missing data wherein the employee has not inserted the occupation of that employer. So only you have inserted the name, the email ID, the phone number. You forgot to insert the occupation. That is a missing data. Noisy data. Containing noise, errors or outliers, salary equal to -10 is a what? It is an error. So we say that this kind of a data is a noisy data. If an employee is being asked name and instead of name he or she puts 1, instead of age he or she puts a -20, what is this? This is an incorrect data. We say this is the noisy data. Inconsistent, containing discrepancies in codes or name, example age equal to 42, birthday is 3/7/2010. If your age is 42, how can your birth date be in 2010? Right now it's going what? 2023 and 2010. So how is it possible that you are 42 years of age? So there is a discrepancy. Was rating 1, 2, 3, now rating ABC. So till now the rating was given as 1, 2, 3 and now the rating is given as ABC. Again, this is a discrepancy. Discrepancy between duplicate records. Incomplete or missing data. Data is not always available. Example, many tuples have no recorded values for several attributes such as customer income in sales data. So in a sales data, the customer's income is what? It is a tuple, but the tuple has a missing value. Missing data may be due to equipment malfunction, inconsistent with other recorded data and thus deleted data not entered due to misunderstanding. Certain data may not be considered important at the time of entry, not register history or changes of the data. Missing data may need to be inferred. How can you handle the missing data? So first is ignore the tuple. So ignore the missing tuple. Ignore the income tuple in the sales data of a customer. Usually done when the class label is missing. When doing classification, not effective when the percentage of missing values per attributes vary considerably. Fill in the missing values manually, tedious plus infeasible. So either you fill in the missing values manually, ask the customer, fill in the values manually, but it is tedious and inflexible. Use a global constant, example unknown, a new class. So if that sales data does not have the customer's income, then in the income column write unknown. So either fill in the income by asking the customer manually or write a unknown. Use the attribute mean, that means take the mean of all the incomes of different customers. So take the addition of all the incomes of different customers divided by number of customers. Whatever mean you get, you write that mean as the income of the customer who has a missing field. Use the attribute mean for all samples belonging to the same class. Use the most probable value, inference based such as Bayesian formula or decision tree. So most probable value means the one which is used again and again is the most probable value. Use that value if you want. So these are all the ways to handle the missing data. Next is your noisy data. Noisy, random error or variance in a measured variable. Incorrect attribute values may be due to faulty data collection instruments. So it can be due to faulty data collection instruments, data entry problems, data transmission problems, technology limitations, inconsistency in naming convention. Other data problems which require data cleaning, duplicate records, incomplete data, inconsistent data. All these will require data cleaning up. How to handle noisy data? Binning. First sort data and partition into equal frequency bins. Then one can smooth by bin mean, smooth by bin median, smooth by bin boundary, etc. So how do you do the smoothing? So you have been given the data, first sort it in the ascending order. Once we sort this data in the ascending order, what do? 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 values are given and you have 3 bins. So 9 divided by 3, that is how much? 3. So each bin can have 3 values. Each bin has 3 values. So how to bin mean? So what will you do? For equal frequency, you will take the first 3 numbers 4, 8, 15, then 21, 21, 24 and then 25, 28, 34. For smooth by bin mean, you will calculate the mean. How will you calculate the mean? Or add all the values, divide by the total number of values. Whatever you get the mean, you will write as this. So how will you do this? So for example, for bin 1, what will I do? I will say 4 plus 8 plus 15 divided by 3. I get that equal to 9. So I will write 9, 9, 9. In the second bin 2, I will do 21 plus 21 plus 24 divided by 3. I get 22. So I will write 22, 22, 22. In the third bin case, I will do 25 plus 28 plus 34 divided by 3. I get 29. So I write 29, 29, 29. Smoothing by bin boundaries. In bin boundary, you should take a boundary. So for example, if I am taking the lower boundary, that is if I am taking 4, then what will I do? 8 is given, right? So 8 is closer to 15 is what? 15 minus 8 if you do, you get 15 minus 8, you get 7. And if you do 8 minus 4, you get 4. So it is closer to 4. So what do I write? 4, 4, 15. Second case, if I say 21, 21 is closer to 21. So I will write 21, 21, 24. So the middle number you will check. 28. 28 is again closer to 25. 25, 26, 27, 28 means only 3. 28, 29, 30, 31, 32, 30, 34, it is 6. So here you have 3, here you have 6. So it is closer to what? It is closer to 25. So I will write 25, 25, 34. So what will I check? I will always check the one closer value in bin boundary. The one with which the middle value is closer, that will be repeated twice. So this is the way I will be handling the noisy data. How to handle regression? Smooth by fitting the data into regression functions, clustering, detect and remove the outliers. Combine computer and human inspection, detect suspicious values and check by human. So, data cleaning as a processor. Data discrepancy detection. Use metadata, example domain, range, dependency, distribution, check field overloading, check uniqueness rule, consecutive rule and null rule. Use commercial tools, data scrubbing, use simple domain knowledge, example postal code, spell check to detect errors and make corrections. Data auditing by analyzing data to discover rules and relationship to detect violators, example correlation and clustering to find outliers. Data migration and integration. Data migration tools allow transformations to be specified. ETL, that is extraction, transformation and loading tools, allow users to specify transformations through a graphical user interface. Integration of the two processes, interactive and iterative, example is potter's wheel. Next we will see the data integration processor. Data integration. So what is data integration? Combines data from multiple sources into a coherent store. So data integration will combine data from multiple sources into a coherent store. Schema integration, example a.customer id equal to b.customer hash. Integrate metadata from different sources. So integrate the data from different sources. Entity identification problem. Identify real world entities from multiple data sources. Example Bill Gates equal to Bill Clinton equal to William Clinton. So you identify the real world entities from multiple data sources. Detecting and resolving data value conflicts for the same real world entity. Attributes value from different sources are different. Possible reasons, different representation, different scales. Example British versus metric unit. So there are certain conflicts. So you have to resolve that data conflicts. So in the metric system it will be different. In the British system it will be different. Handling redundancy in data integration. Redundant data occur when the integration of multiple databases. So redundant data, it occurs often when the integration is there of multiple databases. Object identification. The same attribute or object may have different names in the different databases. So the same attribute or object, it may have different names in the different databases. Derivable data. One attribute may be derived attribute in the another table. Example annual revenue. Redundant attributes may be able to be detected by correlation analysis and covariance analysis. Careful integration of data from multiple sources may help reduce or avoid redundancies and inconsistency and improve mining speed and quality. So correlation analysis, correlation coefficient also called as Pearson's product movement coefficient. So if it is greater, then we say that they are positively correlated. If it is equal to 0, we say it is independent. If it is less, if your value of R is less, then we say it is negatively correlated. So correlation viewed as linear relationship. Correlation measures the linear relationship between objects. To compute correlation, we standardize data objects A and B and then take their dot product. Covariance. Okay, you have a formula for covariance also. Again, positive covariance if covariance is greater than 0, negative it is less than 0, independence if it is equal to 0. So example of covariance, if all the stocks are affected, so suppose there are two stocks A and B have the following values in 1 week. So these are the values of the stock in 1 week. Question, if all the stocks are affected by the same industry trends, will there be a price rise or a price fall? So first we have to calculate what? We have to calculate E of A. How will you calculate E of A? We will only take the x coordinates. So x coordinate is 2 plus 3 plus 5 plus 4 plus 6 divided by the total number, that is 5. So you get answer as 4. E of B will be the y coordinates, that is 5 plus 8 plus 10 plus 11 plus 14 divided by 5, that is 9.6. And then you will apply the covariance formula, that is this formula. Covariance of A comma B equal to E of A dot B minus E bar into B bar. So A into B is 2 into 5 plus 3 into 8 plus 5 into 10 plus 14 into 11 plus 16 into 14 divided by 5 minus, we got this E of A bar and E of B bar. We multiply them, we get the answer as 4. Now because 4 is greater than 0, we say that it is a positive covariance. We say what? It is a positive covariance. So what will happen when the stock prices rise? Obviously, because it is a positive covariance. So we say that A and B rise together, the stock prices will rise. So this is the simple example. It can come for 5 marks on covariance. Next is data transformation. A function that maps the entire set of values of a given attribute to a new set of replacement values such that each old value can be identified with one of the new values. Methods is smoothing, remove noise from the data, attribute or feature construction, new attributes constructed from the given ones, aggregation, summarization, data cube construction, normalization, scale to fall within a smaller specified range. You have the 3 types, that is you have min-max normalization, z-score normalization and normalization by decimal scaling. And we have disintegration, that is your concept hierarchy climbing up. So we will see the example on normalization, min-max normalization. So this is your formula for min-max normalization. So they have given you the income range from this to this normalized value they have given, then this is mapped to. So first you have to understand what is V. V is your mapped to. So V is this minus min. Min is what? Out of these two, the one which is the lower. So obviously this is less. So this is your min. This is your max. So what do? I write 73600 minus, you have the min value 12000 divided by max, that is 98000 minus min 12000 into what is this? New max minus new min, that is 1 minus 0, that is the range. 1 minus 0 plus new min. Now min is what? It is 0. Max is what? 1. So you will do plus 0. So you get answer as 0.716. Z-score normalization. Again, this is your formula for Z-score normalization. So you have been given mu, you have been given sigma, then V is already given to you. 73600 minus mu is 54000 upon sigma is 16000. Answer is 1.225. Normalization by decimal scaling, V dash is V upon 10j, where j is the smallest integer such as max, V dash is less than 1. So next is what? Next is data reduction. Data reduction strategies: obtain a reduced representation of the data set that is much smaller in volume but yet produces the same or almost the same analytical results. Why data reduction? A database or a data warehouse may store terabytes of data. Complex data analysis may take a very long time to run on a complete data set. Data reduction strategies: dimensionality reduction. Example, remove unimportant attributes. Wavelet transforms, principal components analysis, feature subset selection, feature creation, numerosity reduction. Some simply call it data reduction, regression and log linear models, histogram clustering, sampling, data cube aggregation. So data reduction, dimensionality reduction. Curves of dimensionality. When dimensionality increases, data becomes increasingly sparse. Density and distance between points, which is critical to clustering, outlier analysis, becomes less meaningful. The possible combination of subspaces will grow exponentially. Dimensionality reduction. Avoid the curves of dimensionality, help eliminate irrelevant features and reduce noise. Reduce time and space required in data mining, allow easier visualization. Wavelength transformation, principal component analysis, supervised and non-linear techniques. So wavelength transformation, discrete wavelength transformation for linear signal processing, multi-resolution analysis, compressed approximations store only a small fraction of the strongest of the wavelength coefficient, similar to discrete Fourier transformation but better lossy compression, localized in space. Why to do the wavelength transformation? Use hat-shaped fillers, emphasize region where points cluster, suppress weaker information in their boundaries, effective removal of outliers, insensitive to noise, insensitive to input order, multiple resolution, detect arbitrarily shaped clusters at different scales, efficient is complexity of ON, only applicable to low-dimensional data. Principal component analysis. Find a projection that captures the largest amount of variation in the data. The original data are projected onto a much smaller space, resulting in dimensionality reduction. We find the eigenvectors of the covariance matrix, and these eigenvectors define the new space. Principal component analysis. Given n data vectors from n dimensions, find k which is less than equal to n orthogonal vectors that can be best used to represent data. Normalize input data. Each attribute falls within the same range. Compute k orthonormal unit vectors, that is principal components. Each input data vector is a linear combination of k principal component vectors. The principal components are sorted in the order of decreasing significance or strength. Since the components are sorted, the size of the data can be reduced by eliminating the weak components, that is those with low variance. That is, use strongest principal components. It is possible to reconstruct a good approximation of the original data. Attribute subset selection. Another way to reduce dimensionality of data. Redundant attributes duplicate much of or all of the information contained in one or more attributes. Example: purchase price of the product and amount of sales tax paid. Irrelevant attributes contain no information that is useful for data mining task at hand. Example: student ID is often irrelevant to the task of predicting students' GPA. So data reduction can be done using regression analysis. You have linear regression, multiple regression and log linear models. You can do histogram analysis, divide the data into buckets and store average for each bucket. Equal width, equal bucket range, equal frequency. Histogram analysis can be done. So data discretization. Discretization, three types of attributes. Nominal values form an unordered set. Example: color, profession. So we already did this. Ordinal values we did. Military or academic rank. Numeric values, real numbers. Example: integer or real numbers. Divide the range of continuous attributes into intervals. Interval labels can then be used to replace actual data values. Reduce data size by discretization. Supervised versus unsupervised. Split top down versus merge bottom up. Discretization can be performed recursively on an attribute. Prepare for further analysis. Data discretization methods. Typical methods. All the methods can be applied recursively. Binding, top-down split, unsupervised. Histogram analysis, top-down split, unsupervised. Clustering analysis, unsupervised, top-down split or bottom-up merge. Decision tree analysis, supervised, top-down split. Correlation analysis, unsupervised, bottom-down merge. Winning we already saw. We'll see concept hierarchy generation. Concept hierarchy organizes concepts, that is attribute values, hierarchically and is usually associated with each dimension in a data warehouse. Concept hierarchy facilitates drilling and rolling in data warehouses to view data in multiple granularity. Concept hierarchy formation recursively reduces the data by collecting and replacing low-level components such as numeric values for age by higher-level values, concepts such as youth, adult or senior. Concept hierarchies can be explicitly specified by domain experts and or data warehouse designers. Concept hierarchies can be automatically formed for both numeric and nominal data. For numeric data, use discretization methods. So concept hierarchy generation for nominal data, specification of a partial or total ordering of attributes explicitly at the schema level by users or experts, street, city, state, country. Specification of a hierarchy for a set of values by explicit data grouping. Urbana, Champaign, Chicago. So that is what less than Illinois. Specification of only a partial set of attributes, only street, not others, so you're not including other things. Automatic concept hierarchy generation. Some hierarchies can be automatically generated based on the analysis of the number of distinct values per attribute in that data set. The attribute with most distinct values is placed at the lowest level of hierarchy. You have weekday, month, quarter, year. So the country has 15 distinct values, then it has 365, this is having more, this is having still more. So what it is said, most distinct values is placed at the lowest level of hierarchy. So this has the most distinct values, so you can see the number is larger. So it has most distinct values, so place it at the lowest level of hierarchy.